So this is circuit stuff. I'm just gonna apologize right now because we don't have time to do this properly. So your quiz on circuits, and I am going to make it just a quiz this time, is going to be on Tuesday. Oh yeah. So yours is going to be on Thursday. Well, let's make it on Wednesday then. How about?
No. This is like math.
Thank you, Earl. And on Tuesday, Thursday, we'll start the electromag a little bit better. So suffice to say, we have to do this fast. So I'm going to throw a whole bunch of stuff at you, and we'll just see what sticks, and then you can do some problems. Hopefully most of it. Put your hand up if you kind of feel like I know some circuits from before.
Like, not really.
Okay, who is starting from baby steps, like from scratch? Okay, that's a lot. Okay, good. We're gonna go with Alex is a quick learner. First of all, there is current and voltage, right? Put your hand if you can tell me what voltage is.
Potential energy at like 1 point.
What is 1 volt?
Potential difference.
A joule per coulomb, right? So joule is what? Energy, and coulomb is charge, right? So if you think of a circuit like little dump trucks moving through, if you have a cell here, the most basic circuit is 1 cell and 1 load. We call this is a resistor, but we call it a load. Why do we call it a load? Nathan?
It takes stuff.
It takes stuff, yeah. This is where you dump off your load of energy. So if you think of, you got little dump trucks here, and they're loaded up with energy in the back.
Do you have to have a resistor in every circuit?
No, there is a load though, even if the load is just a wire. And so let's say you have, if this is a 3 volt cell, right? And you have 3 joules per coulomb. So the dump truck is like a coulomb of electrons. Okay. So the dump truck is like, it's all these electrons. And this is your 1 coulomb. You can think of a coulomb as like a container of electrons. Anybody know how many electrons in 1 coulomb?
1.6. That's the charge.
Ah, okay, so you know the charge on the electron. So grab your calculator,
1 divided by the charge is in
put in the charge of the electron.
1 over that?
Yeah.
Yeah, so do 1.6 times 10 to the negative 19, and then hit your x to the negative 1 button. So we're going to do 1 divided by all of that. And what do you get?
1.6 times 10 to 19.
No. It should be 6.2, I think 6.25, isn't it?
65 times 10 to the, or 10 to the 18.
Good, 6.25 times 10 to the 18. And so that's electrons in 1 coulomb. Okay, so a coulomb is just a bunch of electrons. It's just a certain number of electrons. This number is kind of by accident. We didn't pick this number. We just picked what an amp of current is. Because when we found out current, we didn't even know it was electrons moving around, right? Okay. In your circuit, your little dump truck, he moves around. And the number of coulombs per second is your current. I love that. So it's, Arlo's got a hat that's blinking.
It's
like,
my hat.
Oh, Sarah's hat is blinking. And it's blinking LEDs, which we're going to talk about later too. So it's very, very appropriate.
So the current is charged over time?
Good. Current is charge over time. So Q is my charge in coulombs, and T is my time in seconds.
And current is I.
Current is I,
That
yes.
makes sense.
It's weird that it's I, but yes, this is current. And this is charge. And so your current is in the unit of amperes. And that was discovered by Ampere back in France in early 1800s, I think. Maybe even before that. Anyway, if you could get in the magic school bus and you could jump into these wires here and get right inside of it, you would see electrons flowing past. And if you could count the electrons in groups of this number, if there was 1 amp of current flowing in the wire, you would count one of these containers of electrons going by every second. Okay. Does that make sense? Okay. So the number of dump trucks, that's your current. What would you say about the current here and here and here?
It's all the same.
It's the same. There's no change in current around a single loop. You have to have a branch in the circuit. So you can think of this as like a road, right? Your road might get skinny, but the number of trucks leaving the factory and entering the factory has to be the same. They don't just disappear. Okay, and so then what happens at your load? What happens to the truck? Yeah, it unloads. It doesn't fully unload, but it unloads most of its energy. Okay, it has just enough to get itself back to the cell. And when it enters the cell, it will be at exactly 0 volts. That's just a fun thing that happens in our universe. It has just enough energy to get around. Okay. It's kind of like a river running to the ocean. It has just enough energy to get itself back to the ocean, right?
So basically, like, you could figure out how much energy the resistor is
Dissipating.
dissipating based on the
Exactly. So if we had a water pump and we took some of the ocean water and we pumped it up to Cypress Mountain, what kind of energy are we adding to the water? Potential, gravitational potential, right? And then if we release it, it has just enough energy to get all the way back to the ocean, right? That's exactly what we're doing here. We're loading the truck with energy. So we're loading our coulomb of electrons with energy, and we're pushing them around and unloading them here. So this is the push up the hill, and then this is falling back to the ocean. Now in a circuit, we make it so that the wires are really free flowing, so it's easy for them to move, and then at the load, most of our energy is being deposited here. Yes, for us?
What if there was another like volts thing right after the load? Could the load just take all of its energy away since it doesn't need as much to get to the next one?
You mean if there was another one right here?
Like right after the load.
Oh, here you go.
Would the load just take everything and then?
We're gonna get to those. We're gonna get to those. And you can even put one in that's facing the other direction, and it gets complicated. But well, I don't want to get ahead.
I thought volts direction didn't matter.
Say that again.
I thought for volts direction didn't matter.
Oh, the direction of a cell matters. This has a long line and a short line, and the reason is because a cell is polarized, right? So the long line is always positive, and the short line is negative. We take current to be in the positive direction. This is very confusing because we know it's actually the electrons that are moving around the circuit, but we just say it's positive. So current is flowing this way in this circuit. Even though we know the electrons are actually moving that way, we say the current is going in the positive direction. Because, as we learned before, in an electric field, it's that positive test charge. That's the direction of the field, right? It's a little bit confusing, but Okay, and so we could find out if I said that this was a 6 ohm resistor, would you be able to calculate the current in that circuit?
It's like volts over current, right?
It's Ohm's law. What is Ohm's law?
It's the triangle.
Volts is equal to the current times.
Yes.
Thank you, Dinger. V equals IR. And so our total resistance in this circuit is 6 ohms, right? Because we only have one. So if you want to find the current, how would you do it?
V over R.
So what is it?
3 over 1 over 2.
So you would say this is 0.5 amps. Yes? So you would say V over R equals I. And our voltage is 3. We don't have any other voltage source, and it's all going to get dropped at this resistor. A little bit left for the wires, but that's negligible. And our resistance is 6, so we'd say 3 volts over 6 ohms is going to equal 0.5 amps. And if you were to put an ammeter anywhere in this circuit, if you put an ammeter here, it would read 0.5 amps. If you put an ammeter here, it'll read 0.5 amps. Okay, anywhere along there. Good so far?
Yes.
Okay. Of course, unfortunately for us, it doesn't stay so simple. We can add resistors and or loads to our circuit. What would you guess is the total resistance of this circuit?
6.
It is 6. So if your resistors are added in series, it's just more resistance. You just add it up. And so when I say Req, this is called equivalent resistance. And so in this case, it's R1 plus R2 plus R3. Oh, sorry. And so this is going to be 6 ohms in this case.
So would I also be equivalent?
No, we don't call it equivalent because there's just one I in this. So equivalent resistance is, now how do I say this? Equivalent means like if there was only one resistor in the circuit, it would be equivalent to a 6 ohm resistor. How do I word that?
It's like there was only one 6 ohm resistance
Right.
instead of 3 2 ohm resistance.
Is the value as if the circuit contained only one. Make sense? Okay, so what is I then in this circuit?
Can you go to the minute?
I is 0.5.
0.5 again, right? So that circuit is exactly the same as the one I drew on the board, really. So you can think of it like cars in traffic. If you have if you're on the highway and then suddenly you have a bridge that squishes the traffic up and you have to drive slowly and then it unsquishes again. It's like, okay, that's great, but now there's another little squishy bridge and everybody has to fit through there again. If you put multiple bridges in a row, it just causes more traffic jam, right? You just add up the traffic jams. Mark?
What if you just have a really long bridge?
Yeah, same. So if you have 3 short bridges of 2 ohms each, is the same as if you connect them all together and you have a 6 ohm one bridge. That was a good question. So that's exactly how equivalent resistance works. It doesn't matter if you space them out or throw them all together, it's the same. Yes, Sherry?
What do you call the
Pardon me?
What do you call the two lines?
Oh, these two? Like here?
Isn't that a battery?
Is that what you mean? Yeah, this is a cell. It's technically not a battery unless you have more than one cell, which we will do too. So like let's say you have a flashlight, which nobody has anymore because it's on your phone now, but if you have a flashlight and you have multiple cells in there, you would draw that like, this. Let's say you had 3 cells. You would draw that like that.
That would be a battery.
That's a battery, yeah. And it's a battery
That has 3 cells.
of cells. That is correct. Do you know why it's called a battery?
It's all.
Ben Franklin, the guy on the $100 US bill, he coined that term because he had a bunch of Leyden jars that he was using for charge, and he lined them all up and connected them like cannons on a ship. And they used to call that a battery because you would batter your opponent with your lineup of cannons, right?
Wait, so technically, we have cannons in our phones.
Yes, definitely you have lineup of cannons on your phone. Okay.
Yeah, or that's okay.
So in this case, just to reiterate, the I would be V over R, which would equal 3 volts over 6 ohms, which again would equal 0.5 amps. And in this circuit, you could still put your ammeter anywhere on this circuit and you would still have a 0.5 amp of current. Okay. If I asked you to tell me how many electrons move through that wire in 1 second, could you find out? Victoria, how would you do it?
You just like half the 6.25 times 10 to the 18.
A golf clap for Victoria. Because this is, if we had 1 amp, you'd have this many electrons go through every second, right? So if you have a 0.5 amp, it's just half that many. If you have 3 amps, you just, yeah.
Wait, what? So amp equals the amount of electrons?
Yes. 1 amp, and this is I would say quite, it's handy to think, when you do circuit electricity, it's kind of handy sometimes to think of the units. So 1 volt is equal to 1 joule per 1 coulomb. Yes? 1 amp, now this is the unit of current.
You do 1 volt over 1 resistor.
Yeah, it's easier to think 1 coulomb over 1 second. So a volt is a joule per coulomb, an amp is a coulomb per second.
But isn't it 1 over coulomb over a second?
For an amp?
Oh, whatever.
No, that the number of electrons is 1 over the
Yeah, so if 1 amp equals that, then that equation doesn't make sense. It has to be 1 over the coulombs over second.
It works.
It works.
Trust me.
Can you show us how it works?
Can I show you how what part?
How can you use charge for time as well as volts and resistance?
Say that one more time.
How like Ohm's law and also the charge of time.
Oh, I see what you mean. Yeah. So you're thinking like, how does this work with these? Yeah, so an ohm, tell me what an ohm would be. If you have a volt
Ohm is
for this, in units, that would be like a joule per coulomb over a coulomb per second, right? So that's a joule per coulomb.
It's joule second per coulomb squared.
Yeah, it would be joule second per coulomb squared, yeah. It's not particularly helpful, but that's what an ohm is. It's a joule second per coulomb squared. That's just confusing. I wouldn't worry about that part. Just forget that exists. Yes, Sherry. You're thinking. Thinking is good.
Over there, like, current is charged with time, which would be measured in amperes.
Yes. So coulombs per second is 1 amp. Yes, that's right. Let's move on a little bit. I'm sorry, I'm throwing a lot at you. What if I draw my circuit like this? I take my 3 2-ohm resistors, but instead of putting them all in a line, I branch them out like this. Is it going to be 6 ohms?
No, it's a different current in each one, right?
So think about our traffic analogy.
Oh, the first one's gonna be 2 ohms, the second one's gonna be 4 ohms, the third one's gonna be
If you take,
You're gonna go to the path of least resistance.
so answer me this. If you're driving down the road in a traffic jam, and suddenly the road splits into 3 roads, is that going to make traffic worse or better? It's going to make traffic better, right? You have 3 different roads to choose from. So is the overall resistance here going to be more or less than the 6 ohms? It's going to be less, right?
But doesn't it all end up in the same place anyways, so?
Yes. So the current coming out of the cell is going to be the same as the current here, right? But the current here and here and here are going to be different because not all the trucks are going through one branch, right? They're going to split. And as Carter says, they're going to take the path of least resistance. Now these are all the same resistances. So they're going to split evenly between the 3 because the skinny little bridge is the same in all 3 areas, but they have 3 roads to choose from. So the traffic is going to be less than it would be if you had to go through all 3 bridges, right? Okay, so what's my equivalent resistance in this circuit? It works like this. It's an interesting mathematical relationship. The REQ for this is the inverse of the sum of the inverses. So 1 over REQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on and so on and so on. Okay. Now,
Why is it inverse?
take your calculator and go like this. Put in the 2. So our first resistor is 2 ohms, right? And then hit x to the negative 1. And then go plus 2 x negative 1 and go plus 2 x negative 1.
One over it.
Now hit answer and then hit x to the negative 1 more time. And it's 2 over 3, right? So your equivalent resistance here is just 2/3. It's quite low. So we can write that out as well. We can say, well, 1 over REQ is equal to 1 over 2 plus 1 over 2 plus 1 over 2. And that's going to be equal to 3 over 2. And so our REQ is equal to the inverse of that, which is 2 over 3. And that would be in ohms.
Where would your REQ be though? In all 3?
Where? In the entire circuit.
wherever.
Yeah, they're going to be in different places, right? Okay, so the reason this is useful is because if we know our sort of total resistance, then which current can we figure out right away?
I initial.
Yeah, we can figure out this I naught, the total current in the circuit. And that current is really gonna stay the same the whole way around. It's gonna be split up.
Oh, you divide it by 3.
Yeah, but that sum is gonna be the same all the way around, okay? So let's calculate that.
So I naught equals 3 over 2 over 3 times 3.
Good. So the I naught is going to be V over R, right? And our total voltage is 3 over our REQ, which is going to be divide by 2 over 3, which is
It's
9 over 2, so 4.5, is it?
Yeah.
4.5 amps. Well, you guys write that down. I want you to notice a couple of things, just conceptually. Look at the circuit we did first. What was the current in that circuit? It was just a half an amp, right? So this circuit has quite a bit more current, yes? 9 times more, actually. That's because every truck has multiple roads to go through now. So we fixed a lot of traffic problems. We have good flow of traffic, right? I also want you to notice that this equivalent resistance is less than each individual resistor. So even though we're adding resistors to the circuit, we're actually lowering the resistance than even if we just had one of these in the circuit. So every time you add a branch, a parallel branch, you actually lower the resistance in the circuit. Because the trucks, if you had just one 2 ohm resistor, all the trucks would have to go through that, right? So if you add something else, another pathway for them to go through, even if it's a high resistance path, you're gonna lower the overall resistance. Yes, Chris?
What if one of the paths doesn't have a resistor? Would the amps then go down? Because there's just a third path with no resistor.
If you have a third path, like if I did one more path of just wire with no resistance,
Would the amps
your
go-
current would shoot up and your resistance would drop down.
So you have more amps.
Tell me why.
No resistance.
Yeah. If I said, hey, there's like 3 bridges off the North Shore, and everyone's trying to get off the North Shore, and all the bridges are clogged, but then I was like, actually, Elon Musk was here and he dug a tunnel down to like San Francisco, and it's like, you know, a mile wide, and everybody can drive down it, then everyone would just go, whoo. Right? And that's what a wire is like. If you click a wire around your resistors, so those trucks don't have to go through a resistor, most of them will just go through the wire because it's such low resistance.
The resistance wouldn't even do anything.
It would do something, but not very much. And that's why, if you're a silly high school student, I wouldn't know anything about this, but if you take a metal coat hanger and you put it across the terminals of a car battery, there's really low resistance in it and you get a really high current. And then your parents are wondering why your bedroom carpet is burned. There's a big black hole in it. So don't do that. Yes, Sherry?
Why do they use it like 2 versus
I can discuss that with you, but it's a long conversation.
Okay.
Yeah. For now, just take my word for it that that's how it works out. Okay. You have the total current. If we know this now, there's a rule that I want to really impress upon your minds, because it's very handy. You're going to have problems like this on the current quiz and on your IB exam. In each branch of a parallel circuit, the voltage drop must be the same.
So 1, 1, 1.
It doesn't even matter what value of resistor there is. The reason for that is because you can't have a truck coming back to the battery with energy.
Oh.
Yes, Beyrad?
So they're all 3/2.
Yes.
And you add.
Yeah, the voltage drop in each one here is 3 volts. Because the truck gets loaded with 3 joules per coulomb here, right? So your coulomb truck goes around, and it has to choose. It might go down this one, in which case it's going to drop 3 volts here and go back to the battery. It might go through this one, in which case it's going to drop 3 volts and go back to the battery. You can't have a truck end up with energy still in it. If it does, it's going to pass it back along. It just doesn't work. You can't have part of the river going uphill back up to the mountain, right? It just doesn't happen. Arlo?
How does a buck converter work?
Oh. I'm not going to talk about that right now. Right here, you have another one of the trucks. Now these 3 are equal resistances, so you're going to find that the current here is equal, but that's not always the case. If these resistors are different, then the current in each branch will be different.
But the volts will be the same.
The voltage drop is always the same. So, if this whole thing has to drop 3 volts, then it'll be a 3-volt drop in each one of the branches. Okay. So what's the current here then? If this voltage drop is 3,
3/2.
it's going to be 3/2. Right? 3 volts, and I is V over R, so 3/2. So you're going to have 3/2 amps here, 3/2 amps here, 3/2 amps here, which add up to
9/2. 4/5.
Can you not just
our total, right?
4.5 by 3 to begin with?
Yeah, you can.
Yeah.
You can. So if your mind works well with proportions, then you don't have to actually do what I just said. You don't have to work out the current in each resistor. You can just say, well, these are all equal, so I have to split my total into 3, right? So I could say, well, 4.5 divided by 3 is 1.5. So this is 1.5 or 3/2. 1.5, 1.5, 1.5, and that's good. Now, if you had, say, 2 and 4,
3/2.
and this didn't exist, you would say, well, this one has to be twice, or sorry, if this was 4, sorry, we should do this.
That would be 3 and then the other one would be
3/2 plus 3/4.
Yeah, but one of them twice has to be twice as much as the other.
That's right. That's right. So if I had a circuit like,
Can't you just do them separately and add them?
yeah, you can. You can. But sometimes it's nice to be able to do it quickly like that. If this is 2 ohms and this is 4 ohms. Both my If this is 2 ohms and the other is 4 ohms, tell me about the current in each of those branches.
Has to be double than the first.
This one has to be twice the amount of that one. Okay.
Oh.
Now, what if I put a resistor here?
Haha.
Haha.
It would just be
Well,
added.
what's the resistance of that?
It would just be added.
Would you capture it?
Now what you do is you say, well, all of this is going to have an equivalent resistance, right? So it's kind of like 2 resistors in series. So you find this total resistance and you add it to that total resistance, and then that's the full resistance of the circuit. Then you find out the total current, you find the voltage drop here, and whatever's left has to be the same in these 2. Do that for me. Take a minute and solve this. What voltage battery do you want? 4 volts.
What's the other?
What's the ohm of this one? 2?
Okay, so our
Okay, calculate that for me.
You want the R equivalents or the?
I want everything. Everything else in the circuit. All the currents and all the voltages and all the resistances. Hey, Sherry. The voltage has to add up to 4. So the voltage drops here and here have to add to 4.
It's 10 over 3. So what's the equivalent to this? So I was 45. So the I initial is.
I don't think I'm writing it.
I mean, I found the I initial. I don't know how to find the Z.
Where did you go?
1.2. Yeah,
Oh, 1.67. Right there.
and then 4 over the
I could be wrong about that, but I think that's right.
So it's 1.2.
Oh, no, it's 2.4.
1.2. Oh.
Really right.
The R is 10 over 3. 4 divided by 10 over 3.
Mr. Esme is 2.4.
Are you sure about that?
Well, no, 10 over 3 is 3.3.
Well, this is 4 over 3, right? This part?
Plus 2. It's plus 2. It's plus 2.
Oh, sorry. Yeah, this is a 2 ohm resistor. Sorry, my bad. So that's 3.3?
Yeah.
Thank you.
How do you know the voltage drops at each one?
You find this one first. So your total current, so this is what I'm doing. First, you find the total resistance of the parallel branches. So you do the inverse of the sum of the inverses, and you get 4 over 3. So this has to have a total resistance of 4 over 3. You add that to the 2, not 1, but 2, and you get 3.3. That's my total resistance for the whole circuit. Why do we care about finding that? Because then we can find the total current, right? So we do the total voltage over that total resistance, and that's going to be 1.2? That sounds about right. So the whole thing coming out of the battery, I would call this I naught, is equal to 1.2 amps. That's going to be the same current in this resistor, yes? It hasn't split up yet.
So the volts is 2.4.
That's exactly right. So V equals IR.
The volt drop is 2.4.
So here, this is going to be 2.4, and actually we should really say negative 2.4, because this is a voltage drop. It's usually not written negative, because everybody knows that a load is a drop, and a cell is an add. But we can do that for now. We can say minus 2.4. And that's just in volts, right? Okay, so we started with 4, but we've dropped 2.4, so how much do we have left? 1.6. In my parallel branches,
How is it negative?
each branch is the same. So this is going to be, well, I'm just going with negatives to show that this is a voltage gain. These are voltage drops. You don't have to put the negative in. Okay. So this is like negative 1.6, and this is also negative 1.6. If you see you have different voltages in parallel branches, you got a problem. Every parallel branch that's beside each other like this has to drop the same amount of voltage. If it's not, you're gonna have trucks coming out of the branch, out of the junction with differing voltages. And that can't be, that can't exist.
0.8.
Arlo, you get that, yeah?
Wait,
How is it 1.6?
shouldn't it be 0.8?
Is it 4 minus 2.4?
No,
What's right?
Yeah, 4 minus this.
Yeah, 4 minus
Since
So
it's
you're-
split between 2, shouldn't it be divided?
No, no. And for us, you just, that's what most people think intuitively. You think, well, shouldn't we have like 0.8 here and 0.8 here? But no, because only some of your trucks are going through this branch. And they have to drop 1.6 to get to 0 to go back. The trucks that go through here are never going through here.
Yeah.
The other trucks will go through here. There'll be only half as many going through here, but they have to drop the same amount of voltage.
So 1.6 over 2 is the current. No, the first one.
For this one, yes, 1.6 over 2 would be your current. So here your I would be,
0.8.
how can I write that? I'm running out of space here. 0.8?
Yeah.
That makes sense.
0.8. No.
No.
0.8. Yeah, 0.8.
Yeah, and then for the next one is 0.4.
And this would be 0.4.
And they add up to the original.
Yeah. 0.4 amps, and so this makes sense because we started with 1.2 amps of current. It comes around and at this junction, 0.8 goes this way and 0.4 goes the other way.
Oh.
That's very cool.
But they both drop 1.6 volts. And then they come back together here and they both have just as enough to get back to the cell and then they're good. Okay.
I think we need to.
We will.
In here.
Oh, you definitely.
So the way we knew how much volts we're dropping here is because our voltage drops have to equal our voltage gain. We only have one cell in this circuit, so we're only gaining 4 volts. So every truck, every Coulomb truck, has to drop 4 volts at some point around here. So we know our current, and so we know our voltage drop at the first resistor. So our trucks have dropped off 2.4 volts at this first resistor. And so they only have 1.6 left, so they have to drop it at whatever branch they choose to go through.
No matter which one they go through, they have to drop over.
Exactly. So even if these are different resistances, it has to drop the same amount of voltage. Now take a look at the current between these two. What do you notice?
And it adds up to 1.2.
It adds up to the total. What else? This one is twice the other. Why would that be?
Because this is the resistance.
Because the resistance is twice as much, right? So if you're driving down a road and you have a fork in the road, and you have a really skinny bridge and one that's twice as wide, what's gonna naturally happen is twice as many people are gonna go through the wide bridge, right? And that's why your current is twice as much over here and a half on the skinny bridge. But they drop the same amount of energy going through. Yes, Faraz?
Let's say there was another resistor past the 2 one. It's like, let's say.
Like here?
No, like on the same.
Oh,
like-
in here?
Yeah.
Oh, yeah.
Would the 2 be 0.8 and then the one after also be 0.8 volts drop?
Yeah, so if you have 2 resistors on one track, so let's do this.
This is one resistor.
Well, each one has like a different voltage.
So if I said,
Yep.
and I'll kind of make this simple for this example, but let's say this was 1 ohm and this was 1 ohm. The total resistance would still be the same, right? Because we had a 2 ohm resistor here. So everything would add up the same. The only thing that would be different is that the voltage drop here, instead of being 0.8, right, it would be 0.4 volts here and 0.4 volts
Would
at
it be
this one.
0.8 because it was 1.6?
Yeah.
Oh, sorry.
Or
The total
it's
drop
just
has to
half.
be the same as the other one, basically. as the
Yeah.
other one.
If this is dropping 1.6, then this whole thing has to drop 1.6. So this would have to be 0.8 and this would have to be 0.8. So that when they come out, they have the same amount of energy at the end. Okay. This is volts. The current through here would still be the same as what we figured out before. So this was 0.4, so this has to be 0.8 amps as well. That's coincidental that they're the same, but
But how could they? Can't you just use like math to prove the 0.8? Oh,
there's lots of different circuits that we can do with this, and you can literally spend your whole career figuring out how to work with these. I'm gonna move on because we have other stuff to learn too. Try this.
Oh, they need to find
No, find
Sherry, you had a question. Here?
Yes.
Because
Not
you.
like why it splits, but like 1.6, 1.6.
Yeah, so your voltage doesn't split. Current is what splits. Voltage has to be equal. So your voltage gain of 4 has to be equal to the total voltage drop. So every truck has to go through this resistor and they all drop 2.4, right? Because they all go through this resistor.
Like, what was the calculation? Oh, no, it's still
Because this is a 2 ohm resistor. And so to find current, we do V over R, so 4 over 2. That's okay. Sorry, it's not V over R. To find this one, we had to do the I times R. We know the I was 1.2. So the 1.2 times 2 is 2.4. That's why this is 2.4. Okay. And then 4 minus that is what you have left to drop. So this is not so easy, right?
Wouldn't there be a problem since the 9-volt one is going straight into the 6-volt cell?
Yeah.
Did you just add them?
No. So what's the issue with this?
9 volts, just going straight to a wire.
You've got a 9-volt pushing current this way, right? And you've got a 6-volt current pushing that way. And so they're going to come around and they're going to meet and oppose each other, right? What do you do? Current can only flow through a resistor in one direction. So
So you have to minus.
this is what we're going to do, and I'm going to erase this, but this is all on video hopefully. So is my phone still videoing?
Yes.
Okay, that's good.
So, would you add the voltage to yourself?
I probably should stop it and start it again. Maybe I'll do that. Because otherwise it'll take too long to upload.
Okay, so all of the 9